Okay, welcome to lecture 15 of digital design and computer architecture. We're going to cover two exciting topics. We're going to start with precise exceptions, which we couldn't cover yesterday in terms of issues in pipelining. But this is going to be a very important issue in out-of-order execution that we're going to jump into as well. So it's really critical to know the notion of precise state and how to handle precise exceptions. So we're going to spend at least half of the lecture on precise exceptions, and then we're going to jump into out-of-order execution and learn how a machine dynamically schedules instructions in an order different from the sequential order that is given to it. So it's going to be a lot of fun. And these are all concepts that are implemented in essentially all modern high-performance microprocessors, out-of-order execution microprocessors today. And they also go beyond what we will discuss, but the fundamentals are the same. Okay, let's start with precise exceptions. That's 15A. Remember, these are readings. And as I mentioned, the readings this week and next week at the bottom over here are the things that you should really read for out-of-order execution and as well as precise exceptions, etc., especially the Smith and Sohi reading down here. Okay, so this is our agenda. Remember, we covered pipelining and issues in pipelining this week and earlier last week. What is left is state maintenance and recovery, which is essentially precise exceptions, which we will cover. But before I start, I will jog your memory as to what we covered. What we covered in the last two lectures were quite fundamental, essentially. We talked about dependencies, and we talked about anti and output dependencies, that they are easier to handle. We're going to see another example of why they're easier to handle by renaming them today. And we talked about how to handle flow dependencies, and there are 6 fundamental ways. We talked about 4 of those ways in detail: detect and stall, detect and forward, detect and eliminate at the compiler level, let's say, and do something else, fine-grained multi-threading. We did not talk a lot about prediction, value prediction, but we gave the basic idea. So it's good to consider that and think about that going into the future. And now today, finally, we're going to talk about detecting and moving the dependent instructions out of the way so that we can fetch independent instructions into the pipeline. And remember that we finished with fine-grained multi-threading. This is a really important topic. And we also discussed modern GPUs are fine-grained multi-thread machines. We're going to get back to that when we cover GPUs. But there's a lot more on multi-threading, actually. This is one version of multi-threading, fine-grained. There are different granularities of multi-threading. There's also hyper-threading, like simultaneous multi-threading, for example, where you can execute instructions from different threads at the same time concurrently in an out-of-order execution machine. I'm not going to cover all these different notions of multi-threading that are employed in systems. But if you're interested, you can refer to past lectures, and there are quite a few of them, and I've listed them over here. And if you're really interested, you can actually look at a very detailed, interesting treatment of different ways of doing multi-threading, what its different use cases are for, etc. in these lectures. I will give you one food for thought, actually. You can actually use multi-threading for detection of errors in a program, hardware errors, let's say. So if your hardware is faulty, if you don't trust it completely, why don't you execute the same thread twice concurrently in a multi-threaded hardware and basically compare the results of every single instruction one by one? And that's the idea of fault tolerance, redundant execution, more specifically. If you do that on multi-threaded hardware, you don't lose that much performance. Of course, you do redundant execution, so there are power concerns. But if one thread gets a fault, you can detect it, assuming the other thread doesn't get the exact same fault at the same time, right? So multi-threading has many, many use cases, as we have discussed, we have not discussed, but as these videos discuss. So if you're interested, there's a lot to think about over here. And multi-threading is a concept that's employed in essentially all modern microprocessors. GPUs employ a fine-grained multi-threaded version, for example. As we mentioned last time, Sun Niagara employs also fine-grained multi-thread version. Many existing Intel and AMD processors employ hyper-threading, for example, which is simultaneous multi-threading. And some other processors also employ a similar version. Switch on event multi-threading, for example, if you get a long latency instruction, switch to a different thread is another form of multi-threading. You don't do it every cycle, but you do it when you get a long latency instruction. Okay, So I wanted to mention the importance of multi-threading before we jump into the next topic, which is essentially precise exceptions. How do we preserve the sequential semantics of the von Neumann model that we have been assuming essentially in our classes when we're designing the microprocessing paradigms? Okay, so this is best understood with one concept that's called multi-cycle execution, which we have not covered, but I'm going to introduce right now. Basically, in pipelining, there's one problem that we have not discussed, and that's the concept that not all instructions actually take the same amount of time for execution in the execute unit. For example, an integer add instruction may require only one cycle, right? But a floating point divide or a floating point divide instruction may require 60 cycles of execution. Now you have a problem, right? How do you design the pipeline to ensure that these instructions execute without disturbing each other? And one option is basically saying, okay, I have the longest latency instruction that takes 60 cycles. Every instruction should take 60 cycles in the execute stage, because we were just talking about the execute stage. This sounds terrible, right? It feels almost like we're getting back to the single cycle processor where we're dictating the latency of an instruction based on the latency of the worst case instruction. Of course, it's not as bad because we're doing pipelining. You can increase throughput still, even though latency increases, but you run into a lot of issues like the data dependencies become problematic in a deeper pipeline. So basically, people have developed the idea of multi-cycle execution to handle this. And the idea here is to have multiple different functional units that take different number of cycles. These are specialized for different instructions. And the pipeline now looks a little bit more complicated than what we have seen before. You don't have a single cycle execute unit because some instructions require many cycles, actually. You have many different functional units, execute stages, if you will. You still have in-order execution, meaning you basically send the instructions to the execution units in order, in program order. But an integer add may take only one cycle. An integer multiply may take only 4 cycles. An FP, floating point multiply, may take 8 cycles. A load or store may take as many cycles as it needs. It may take 2 cycles if it's a cache hit, which we will discuss later. It may take 80 cycles if it's a level 3 cache hit. It may take hundreds of cycles if it actually has to go to the main memory, DRAM. And in real systems, it takes hundreds of cycles to get data from DRAM, dynamic random access memory. For example, one data point for you is Xbox 360, which is an old machine right now, clearly for gaming. A DRAM access, a main memory access, costs 650 cycles. And this was not a very high frequency machine by any standards at the time. But even then, it cost 650 cycles to get data from memory. So clearly, this sort of multi-cycle execution with multiple functional units enables you to actually have a better pipeline. Why? Well, each of the execution units actually can be pipelined or not pipelined. For example, multiplier can be pipelined or not pipelined. It doesn't matter. But now what we're doing is we're letting independent instructions start execution on a different functional unit before a previous long latency instruction finishes execution. For example, if we have an FP multiply, let's say, we basically enable other instructions to go to different functional units potentially, right? As opposed to waiting for the previous instruction. And this way, independent instructions can execute concurrently in these different functional units. But they still finish, they need to still finish in order. I have a question mark over here because that's the question mark that we're going to deal with in this lecture. How should they finish, basically? For example, integer add finishes after one cycle, right? Should it write its result to the register file? And we will see that that will cause problems. So we still want to preserve the in-order execution semantics of the von Neumann model. And the question mark is, what do we do with this question mark stage over here? And that's the essentially what we're going to cover in this lecture. Okay, so basically, this is the problem. We have multi-cycle execution. Instructions can take different number of cycles in the execute stage. And I've given you one example over here, integer add versus integer divide. Integer divide takes, in this particular example, 8 cycles. Okay, let me make sure it's 8 cycles in the execute unit. You can see that. And it has its own execution unit. Integer add takes 1 cycle. And you can see another instance of integer divide over here. It takes 8 cycles. Integer add takes 1 cycle. And assume that these other instructions that I don't depict over here are independent of everything. So all instructions are independent. Let's assume that for the sake of this particular example. basically the question is, what is wrong with this picture in a von Neumann architecture? And hopefully you've spotted what is wrong. It has to do with these write back stages, basically. So if you look over here, the divide instruction, you can see that each instruction is admitted into the pipeline sequentially. It's decoded sequentially. It goes into its execution unit sequentially. So that's perfectly fine. But yes, write of the second instruction gets executed first, as one of your colleagues mentioned. Basically, this second instruction writes to the register file before the first one writes to the register file. In fact, not only that, the third instruction also writes to the register file before the first one does. The fourth instruction writes to the register file before the first one does. The sixth one writes to, and seventh one write to the register file before the first one does. So basically, we're updating the architectural state out of order. And clearly, that's not allowed in a von Neumann architecture. Right? We said von Neumann architecture preserves sequential semantics to make the life of the programmer easier, right? As a result, we will discuss why we really want it in this lecture also. But now we're updating the architectural state out of order, which really breaks our sequential semantics. Right? That's not good, and that is exactly the problem. So we would like to somehow make sure that architectural state is updated in order also. And that's the subject of this lecture. But before I go into why this should be the case, how we can enable this, we should also talk about why this makes sense to do. So before that, I think there's one question over here. I need to handle the questions over here so that they don't get into the way. Basically, how can an instruction stay in the same part of the process if it takes multiple cycles for execution? Well, it can stay because you may actually latch intermediate results, right? It could be a pipelined execution unit. So if you have eight cycle pipeline divide unit, for example, then it's just like another pipeline stage. You have 8 stages over here. If it's not pipelined, you need to make sure that you have a signal that says execution unit is done, basically. So there are multiple ways of handling it, just like we discussed with memory or any other pipelined execution unit. Okay, so we discussed what is wrong. But basically, sequential semantics of the ISA is not preserved. And there's a good reason why to preserve it, because what if this divide instruction incurs an exception? So you can look at this divide. It didn't update the architectural state. 3, 4, 5 instructions updated the architectural state. At the end of the execution of the divide, in the last execute stage, we find out that divide caused an exception. Exception is an exceptional condition, basically a problem with the instruction, right? Okay. And one example of an exceptional condition in the divide instruction is divide by 0. So what if one of your arguments was 0? If you're, well, the denominator is 0, right? If that's the case, if you're dividing by 0, then the instruction is undefined. Essentially, the result of the instruction is undefined, right? And if you have, you basically cannot execute that instruction, and the program cannot continue with that result, in a sense, because the value of R4 should be really undefined. Now, this is a problem, and we should really handle it in sequential order in the von Neumann architecture. But what we've done in this pipeline is we've finished other instructions and they've updated the register file. Now, the problem is we should really have stopped when the divide, when we figured out that divide had an exception. Why? Because this is a problem, right? You should not really continue execution if one instruction really faulted. Now, what might happen is the programmer may have written an exception handler where if you get a divide by 0, somehow the program should do something else. Okay. Or the programmer wants to debug the program, right? Because you actually had a divide by 0 exception, and you need to somehow figure out what went wrong in your program. But debugging becomes harder if later instructions actually updated the registers, because now the programmer cannot reason about what's going on in the machine, right? According to the programmer, this divide instruction shouldn't have finished. Okay, it didn't finish, but no later instruction should have finished also. If some later instructions finish, now debugging becomes very hard because because essentially the programmer now needs to reason about what went inside the machine, right? Now we've broken the abstraction of the von Neumann model. Okay. Okay, I think there are some questions over here, but I think people are answering them, so I'm not going to go into detail. But basically, there's a suggestion, can't we just flush the instructions? But no, you cannot, because you already wrote to the register. So one of the students answered that, right? That's the problem with this picture. You already wrote to the register before you determined that divide instruction should not have finished. Okay, so this is one example, certainly, of why you should not do this. And we're going to see other examples. So basically, I've introduced the concept of exceptions, but let me go into this a little bit more. So exceptions and interrupts, these are two different things. Unfortunately, in the field, some people call both of them exceptions. Some people call both of them interrupts. But I would like to distinguish, because of principles and because of the reasons that these are different, that they're different things. They may be handled in similar ways, depending on what you do in the machine. But essentially, both of these exceptions and interrupts cause unplanned changes or interruptions in program execution, like the divide by 0. You should not continue the program in that case. You should do something special, right? It could be that, I mean, there might be other examples, like we'll cover virtual memory, for example. And if the memory location that the load is addressing is not in physical memory, that leads to an exception. Or you can get an access protection exception. So you may be touching some memory that this program is not privileged to touch. And that leads to an exception. So these are all different kinds of exceptions that might happen in a real system. And you should not continue execution after that point. In fact, you should not read or write any location after that point, because you may lead to security issues also, like we briefly alluded to at the beginning, right? If this was a load instruction, if it was going to get a security exception, meaning you're not supposed to access the values, later instructions should really not continue in some way. Okay, so basically, the distinction between exceptions and interrupts is that exceptions happen due to internal problems in the execution of the program. That's why they're called exceptions. Essentially, these are really internal to the instructions themselves or the data values that you're dealing with within the program itself. These are not external to the program. Whereas interrupts are external events that need to be handled by the processor. In a sense, they have nothing to do with the program. In fact, they do have nothing to do with the program. But they're called interrupts because of the von Neumann model. In the von Neumann model, we assume that we have a single processor, right? And whenever an external event happens, the processor needs to process it. And because we have only single processor, we have to interrupt the program that's executing in the processor. If we didn't have a single processor, we didn't need to interrupt that processor, perhaps. Or if we didn't have the von Neumann model, if we had a data flow model, we didn't need to interrupt anything because everything would be part of a huge data flow graph. An interrupt would be an input coming into a data flow graph part that handles external events, right? So the notion of interrupts themselves itself is actually a very von Neumann or sequential thing. You're assuming that the processor is executing sequentially and some external event has to interrupt it. If you're thinking parallel or data flow, the notion of interrupt doesn't exist. But if you're, well, the notion of external event exists, but the notion of interrupting the flow of execution of a program doesn't necessarily exist because everything is a data flow graph, if you will. But exceptions exist. Exceptions exist in all paradigms because it's really inherent to what you're doing in the instruction, right? Divide by 0, you can get that in a data flow machine also. You can get that in a multiprocessor. You can get that in a GPU, and you have to handle it somehow. And that's the key distinction between exceptions and interrupts, whether they're internal or external to the process, to the program that's executing. And that's exactly why we should not call them the same thing, basically. But you will see that there are many ISAs that already made the mistake. Okay, so both exceptions and interrupts require some processing, basically. When they happen, you need to stop the current program somehow in a von Neumann model. You need to save the architectural state of the program at that point. You need to handle the exception and the interrupt, switch to some handling routine, or halt the program if there's no handling routine, for example. If it's an exception, you halt the program. If it's an interrupt, you don't need to halt the program because it's external, right? And then you return back the program execution, if possible, and if it makes sense. So this is how interrupts and exceptions are handled in general. Now, let me go into a little bit more detail. This is general, of course, but there are differences. So exceptions and interrupts are different from each other in 4 different major aspects. Cause is the key. Exceptions are internal to the running thread. Interrupts are external. And hopefully we've nailed that. As a result of this, when to handle them differs. So exceptions, for example, when you detect them, you got to handle them in general. And of course, the exception is known to be real, meaning non-speculative. This means that you should be confident that the exception is actually going to happen for sure. It's not because of an instruction that you fetched on the wrong path because you mispredicted the branch, for example, right? You should really handle the exceptions when you know that the instruction is the oldest in the machine and it's not going to be flushed. And this is one key principle, basically. If you handle the exceptions on a speculative path, this makes no sense, right? Because the instructions, earlier instructions, did not even finish yet, and you don't even know whether this instruction should have been fetched and executed. So if you handle the exceptions in a speculative manner, you're actually violating the von Neumann model also. So you need to handle the exceptions when you know when this is the instruction that's the oldest in the machine. Okay, so that's going to be even more clear when we discuss reordering later on. But interrupts, you have a lot more slack actually. It's because interrupts are external. There's no urgency. There's really no urgency from the perspective of the executing thread to handle them. There may be urgency from the perspective of the system, which is a totally different question, right? System may say, oh, I'm running out of battery, for example. I have to interrupt what's going on in the processor and save the state, blah, blah. Basically get ready for system shutdown, right? That is a high priority interrupt. You may need to handle them, handle such interrupts at high priority. But usually it's handled when convenient. The user inputs something into the keyboard, it's waiting in the buffer, and the buffer is not anywhere close to full. Okay, just let it wait until I finish this thread or finish some more instructions in the thread. So interrupts basically have different priority levels for sure. Certainly the battery low system shutdown interrupt could be a really important interrupt. Another important interrupt is a machine check interrupt. It's called machine check exception, unfortunately, in some cases. In fact, it's better known as a machine check exception, but it's really an interrupt. And what it says is something has gone wrong somewhere in the machine. And let me give you an example. Maybe you got an error in your memory, for example. While the memory was trying to figure out whether there are errors or not, it says, oh, okay, some bits are problematic. I discovered some errors. So memory can be doing this periodically, for example. And you get a machine check interrupt saying, okay, I have some error in memory. And this is usually high priority because if you don't deal with errors, they may accumulate and they may actually cause much bigger problems later in the execution of the program, this program, or some other program. So basically, different interrupts have different priority levels. Have you discussed the power failure? Power failure is another one, certainly, that's high priority. Okay, so when to handle varies between interrupts, but in general, exceptions, it's part of the instruction that you're executing, and you have to handle it. Meaning, if you get an access permission failure, for example, when you're trying to access memory, you'd better handle it because something wrong happened potentially with that instruction, right? And it doesn't make sense to continue executing later instructions that may depend on this instruction. Okay, so I said except for very high priority ones, for example, power failure and machine check error, as we discussed. So the priority of exceptions versus interrupts are also, as a result of the cause, very different. So the priority of the exception is usually the same as the priority of the process. If this is an important process, because the exception is internal to the process, the priority is also important. If it's not an important process, maybe you don't care about the exception as much, right? And the priority of the process may depend on how much user assigns priority to the process, of course, right? Or the system assigns priority. But in case of interrupt, it depends. It's completely independent of the process. It's really dependent on the nature of the interrupt, right? And this goes back to the cause again. Okay, finally, handling context. I'm not going to spend much time on this, but how do you handle this interrupt versus exception? Usually, because exceptions are internal to the process, the context is the context of the process. So the programmer can deal with the exception, for example. Let me put it that way. Whereas when an interrupt happens, the context is really the system. For example, you get a timer interrupt, and that timer expired, and timer says, the system needs to do some backup tasks, for example, every 10 milliseconds or so, or it needs to schedule the threads that are running in the operating system every 10 milliseconds or so. The context is really complete system, right? There is no programmer because the interrupt really associated with the system itself. There's no single program that the interrupt is associated with. True for power failure, true for machine check. So the context of the interrupt is usually system, whereas the context of the exception is usually the process. As a result, when you're writing programs, for example, you can write your own exception handlers. You can say, oh, if I get a divide by zero error, I'm going to do this. I'm going to check these conditions. And based on that, I'm going to re-execute some parts of the program, for example. You can write that handler yourself. In fact, if you've done programming in Java, for example, you may have used try-catch blocks. They're essentially exception handlers at the programming level, which may be implemented at with this kind of exception support in hardware as well. Okay, so this was important context to cover. But basically, in a von Neumann architecture, you need to have precise exceptions and interrupts. What does this mean? That's the subject of this lecture. The architectural state should be consistent or precise when the exception or interrupt is ready to be handled. It doesn't matter whether it's an exception or interrupt. You need to obey two conditions, basically, for the architectural state to be consistent. Basically, you need to have a clean state, clean separation between the instructions that's causing the exception, and all of the instructions that are coming after and before. Basically, what does this mean? All previous instructions should be completely retired, finished. They've updated the architectural state. But no later instruction should be retired, meaning they should not have touched the architectural state, registers, or memory at all. And from the perspective of the programmer, this is really important, because now you can pinpoint the fact that this is the point where my program stopped. For whatever reason, it could be an exception or interrupt. Of course, the programmer usually deals with the exception, so it's easier, right? This is the load instruction that caused an exception. And I know that all instructions prior to this load have finished execution. They have updated the architectural state. So now I can debug. I can check whether the architectural state is updated correctly, first of all, whether I got some wrong data value for whatever reason. And I am guaranteed that no later instruction is finished. This is good because I have a clean state at the boundary of this load instruction, right? And that enables the programmer to be sanely debugging their programs. And we'll see this in a little bit also. But this is basically the two conditions that are required for precise exceptions or precise interrupts. And you need to have a precise architectural state at the boundary of the handling of the exception and the interrupt, essentially. Okay, so I said I use the term retire over here, and let me define it a little bit more clearly. This is called also commit. Essentially, this means that finish the execution and update the architectural state. Okay, and we're going to use the term retire many times later on because instructions will retire or commit in the order that the program is written. And that's what we're going to support in this first half of this lecture. This is also called graduate. I don't like that term as much. It's like graduating from a college or something. It's kind of similar, I guess. You're graduating the instruction by updating the architectural state. But I like the term retire and commit more. And these are more commonly used as well. Okay, so basically, how do we handle exceptions in pipelining? Essentially, when the oldest instruction ready to be retired is detected to have caused an exception, there's some control logic that first ensures the architectural state is precise, meaning register file, program counter, and memory are all updated at the boundary of this instruction, such that all earlier instructions finished and updated the architectural state, and no later instruction updated the architectural state. At this point, you flush all younger instructions in the pipeline because you need to handle the exception, or you need to handle the interrupt at the time you decide to handle it, right? So flush actually has a place, as one of your colleagues mentioned, but it has to happen at a precise state. After that point, the machine or the control logic saves program counter and the registers, architectural registers of the executing thread as specified by the ISA. So usually instruction set architectures specify what architectural state needs to be saved and where it needs to be saved also. We're not going to deal with that at this point. And then the control logic, the exception handling control logic, redirects the fetch engine to the appropriate exception handling routine. This could be also interrupt handling routine, but I'm giving you the example from exceptions here. Interrupts are handled in a very similar way, actually. But in this case, we're assuming that the oldest instruction that is ready to be retired is detected to have caused an exception. And you should check only the oldest instruction for exceptions, because later instructions may all be flushed, right? Okay, so why do we want to have precise exceptions? So now that you understand the context and how we handle it, first of all, let's discuss why do we want precise exceptions. And the first answer is very legalistic, meaning that contract-based, right? Semantics of the von Neumann model ISA specifies it, right? Remember von Neumann versus data flow? Von Neumann says, I have sequential execution. No instruction should have started before this instruction finished. And I want to maintain that to keep the programmer sane from my perspective. And if you actually violate precise exceptions, you're violating the von Neumann model, which means that you're violating the ISA contract. And as a result, you're not designing a machine that is correct. Of course, on the other hand, the data flow machines don't have such a contract. There's no precise exceptions in a data flow machine, and when the ISA is data flow. And as a result, data flow machines are actually quite hard to program and debug. Okay, but of course, this is a legalistic reason. Then you can always ask the question, why is there this requirement of precise exceptions in the von Neumann model? And the argument is that it aids debugging, basically. As we said, the programmer can now reason about where the program had an error and basically can debug, assuming that all prior instructions in sequential execution stream finished and no later instruction has started. If this is not maintained, the programmer can go crazy because they don't know which later instructions actually finished, right? If you don't maintain precise exceptions, you need to somehow communicate which later instructions have finished. Even if you communicate that information correctly, the programmer can go crazy because now they need to figure out which instructions executed, which instructions didn't execute, and how should they have executed. So it becomes very hard to debug the machine. And actually, people have tried not having precise exceptions in high performance machines in the past. What they did was they actually dumped the entire pipeline state in memory. And whenever there was an exception, the programmer was supposed to examine the pipeline state and figure out what is going on. Of course, this is very difficult for a regular programmer, right? And as a result, programmers went crazy, and this was a bad idea. I mean, maybe if you're an extremely expert programmer, like 0.1% of all the programmers who know exactly what's going on in the pipeline, you may be able to do that. It will still take you a lot of time compared to having precise exceptions. But in the end, software debugging, you could enable that in different ways. But precise exceptions makes it really easy to debug your programs. Okay. Also, precise exceptions enables easy recovery from exceptions, as we discussed, right? You just need to take the steps that I mentioned over here, because you're assuming no later instruction retired. You just flush them, right? You can just flush them. And then when you come back to the program, you can re-execute all the instructions, right? Assuming that you come back to the program after fixing the condition that caused the exception, right? So handling or restarting from after what happened in the exceptions becomes much easier. You don't need to figure out which instruction executed, which instruction updated the architectural state. All of that is gone. Everything else after the exception is flushed, and nothing else before the exception. It is not the case that anything else before the exception did not finish. So you have a very clean boundary. Similarly, it enables easily restartable processes for the same reason, essentially. I'm not going to go into the details, but these two are very tied to each other. It enables also one other thing, traps into software. Basically, this is also interesting, which we did not spend a lot of time on this, but basically you may have some opcodes that are not implemented by hardware, but you may basically have an undefined instruction from the hardware's perspective. And when you actually decode this instruction, you figure out that this opcode is not supported in hardware, you throw an exception. And now, if you have a precise exception, you're guaranteed that no later instruction finished and all prior instructions completed. The software can emulate this instruction itself with that safe assumption. So you still have the sequential execution model for that instruction that you did not implement in the hardware, but the software can emulate it within the paradigm of sequential execution, essentially. So basically, not having precise exceptions breaks sequential execution. And as a result, you cannot do this trap into the software like software implemented opcodes easily. Okay, so let's talk about how to ensure precise exceptions now. Hopefully these are clear. And some of these topics actually require some thinking, like enabling easily restartable processes or recovery from exceptions. I would suggest you think about them in more detail if you didn't fully understand them at this point. But basically, let's take a look at how we ensure precise exceptions. Let me talk about how to do it in a single cycle and multi-cycle architecture. And it's easy to do in single cycle and multi-cycle machines. Basically, in single cycle machine, there's no problem because instruction boundaries are cycle boundaries, and you handle the exception at the cycle boundaries, basically. In multi-cycle machines, you can add special states in the control finite state machine that lead to the exception or interrupt handlers. I'm not going to go through this in detail, but this is very easy in a multi-cycle machine. And you can switch to the handler only at a precise state, basically. For example, before fetching the next instruction, or before decoding the next instruction. You could actually decide wherever you do it before basically doing any harm at a precise boundary, right? Let me give you the example from your book. This is actually from your book, section 7.7, which is a very short treatment of exceptions in a multi-cycle microarchitecture. And you can see that after the decode stage, for example, you can see that, ignore this MFC op over here. That's something else that your book adds. But if your op is something that's not defined, you go into a state that's called the undefined opcode state. And this basically redirects the pipeline to an exception handler. Basically, it says, even your book basically confuses exceptions and interrupts, unfortunately. But basically, there's a cause of exception that needs to be raised. And you basically change the program counter based on the cause of the exception to a particular exception handler, which in this case will handle the undefined opcode. And you may actually go to some place to fetch the instructions. And this may actually be a place where you emulate the instruction in software, right? Which I'm not going to get into. But you can see that we easily add another state to handle the undefined opcode exception when you decode an instruction. Some bits basically that you fetched are garbage because they don't correspond to any opcode that's implemented. If that's the case, it's undefined opcode, and you need to handle that exception, right, in the decode stage. Also, there are other exceptions that are raised. For example, an integer, an R-type operation may cause an overflow. If it's not the overflow, then you go to the regular states. If it causes an overflow, then this is another type of exception. Unfortunately, your book again says interrupt, but it's an exception, right? Because it's really internal to the process. You basically change the program counter in this state to the exception handling routine. And you can see that you're writing to the PC here so that you go to the exception handling routine in the next cycle, if you will. And you, of course, need to provide the data path support to support overflow and undefined instruction exceptions. And you can see that the exception PC is provided into the program counter over here. I'm not going to go through the details of this, but this enables that you change the program counter to the exception handler PC depending on the cause of the exception. And you can imagine that this logic can potentially get complicated if you have hundreds of possible exceptions, for example. Now your program counter can go to 100 different potential places, right? And I'm not going to go into this. Modern machines actually solve that problem by doing something called vectored exceptions. They basically do not have a huge mux over here, but they determine the address of the program counter that they need to jump to based on a vector table, let's say, depending on the type or the code of the exception. Again, if you didn't understand that, don't worry about it. It's basically, it's basically an advanced concept that your book also doesn't cover. Let me take a look at one question over here. How do we ensure no further instruction is retired if you have several execution units with different number of cycles? So we're getting to that, basically. Okay, so now I'm getting to this one, basically. So it is easy in multi-cycle and single cycle. How do we actually do it in multi-cycle execution in a pipeline machine? As I said, this causes more complications because we've already written to the registers over here. So let's take a look at how we can potentially handle it, right? Well, one way of potentially handling it is to make each operation take the same amount of time. I've already dismissed it earlier, but let's take a look at it again. If you do this, if your longest operation is 8 cycles, then you basically make sure that all operations take 8 cycles, okay? Unfortunately, this is not a good solution as we discussed, because now your worst case instruction latency determines your pipeline depth and also all instructions latencies. Now, think about worst case instructions. What about memory operations? If a memory operation is supposed to take in the worst case 500 or 650 cycles in Xbox 360, for example, do you make every functional unit take 650 cycles? Now, that sounds quite, let's say, bad, right? That's a very bad trade-off because you're increasing the latency of every single instruction, and you're probably degrading the throughput of your pipeline significantly because how do you handle the data dependencies? You're basically complicating your pipeline. So this is not a good solution. Even though this is a solution to ensuring precise exceptions, you're basically ensuring that every instruction is taking 650 cycles and finishing writing to the architectural state at the end of 650 cycles. But that's not a good solution, basically. So let's talk about some realistic solutions. Basically, people have proposed very interesting solutions to this problem. One is called the reorder buffer. And the basic idea is very simple. Before you write to the register file, reorder the instructions. Basically, enforce the sequential order as you write to the register file. That's the idea. And memory, of course. Right? And we're going to see how to do that. But there are also other approaches like history buffer, future register file, and checkpointing, which I'm not going to talk about. This suggested reading over here actually talks about reorder buffer, history buffer, and future register file. It doesn't talk about checkpointing, but suffice it to say that all of these approaches are actually employed in combination in existing processors, maybe with the exception of some history buffer. Certainly, reorder buffer, future register file, and checkpointing are employed in existing microprocessors with some variations in the proposal. But I'm going to refer you to some other lecture to look into history buffer, future register file, and checkpointing. We may actually cover the future register file later on a little bit in conjunction with out-of-order execution. But reorder buffer is important because it actually exists in multi-cycle execute that we have seen. It also exists in out-of-order processors, as we will see. Okay, so see suggested lecture videos from spring 2015 for these, which are also quite interesting. Let me take another question over here. Could we make the length of the instruction dependent on the minimal ending time of currently executing instructions? So yeah, now you're complicating the machine. Potentially, yes, but you don't solve the problem when an instruction takes very long, right? Because now you need to check for, you're basically making the pipeline control much more difficult, if you will. Okay, so I'm going to give you a more general solution that works with many, many different systems like out-of-order execution as well. So basically, this is our solution one. I don't know why recall is here. Recall should not be here, but basically, let's do this. Essentially, the idea is reorder buffer. We're going to complete the instructions out of order, but reorder them before making results visible to the architectural state. So basically, it will look like this. We're going to decode the instructions in order, put them into the functional units. But while we're decoding them, while the instruction is decoded, it also reserves the next sequential entry in the reorder buffer. Basically, reorder buffer is a sequential list of instructions. The oldest instruction is at head, the youngest instruction at the tail, and you insert the instruction to the tail so that you ensure that you keep the order of the instructions that you have in the pipeline. Basically, it's a list of instructions in the pipeline in sequential order, right? So you insert the instruction when it's decoded in sequential order into the reorder buffer. When the instruction completes, it writes its result into the reorder buffer entry, but not to the register file. Okay, basically, instruction can complete in any order. It writes its result into the reorder buffer, but it doesn't update the register file immediately. When the instruction becomes the oldest instruction in the reorder buffer, which means that it's the oldest instruction inside the machine itself, then you check for exceptions. The control logic checks for exceptions. If the instruction is completed without exceptions, then the result of the instruction is moved to the register file or memory at that point in time. Okay, so hopefully this is clear that, and this is clear that it works conceptually, right? You have a ordered list of instructions in the machine in sequential order, and you form the sequential order as the instructions are decoded. Instructions can complete in any order, out of order, and they write their results into the reorder buffer entry. And when the instruction is the oldest in the reorder buffer, then you move the result to the architectural state, which is the register file or memory. Okay, so basically, conceptually, it's very simple. We're going to go into a little bit more implementation details, which is going to be important when we talk about out-of-order execution as well. So basically, reorder buffer buffers information about all instructions that are decoded but not yet finished, retired, or committed. Remember, we said retired as updated in the architectural state. So let's talk about what's in a reorder buffer entry. So somebody asked, so do you also have registers in the reorder buffer to remember the results if one of the instructions finishes early? Absolutely. So you basically have data values that are supposed to be written in the reorder buffer. So you're getting ahead of the slides, which the slide basically answers your question, hopefully. Basically, reorder buffer entry needs to store the destination register ID of the instruction and the value of the instruction. If it's a store, it needs to store the store address and the store data. It needs to store the program counter of the instruction for exceptional conditions and whether the instruction has generated an exception, because you need to decide whether or not you handle the instructions exceptions when the instruction is the oldest in the machine, right? You handle the exceptions at that point in time. And you also need to have some valid bits to make sure that actually the destination register is actually finished or written into by the instruction. Right? And then you also need to have a valid bit for the reorder buffer entry itself, right? Because you may not have allocated the reorder buffer entry. Right? So basically, you need to have everything that is required to correctly reorder the instructions back into the program order. These are the control bits over here and the valid bits over here, and the head and tail pointers into the reorder buffer. It's actually a circular list that needs to be implemented in hardware. And everything required to update the architectural state with the instructions results if the instruction can retire without any issues, these are the blue parts over here, meaning the register value, register ID, you need to have them because you're writing to the register file at that time. The memory address and memory data, you need to have them, and you need to have val bits associated with them saying that these results are completed, right? Because reorder buffer entry is allocated, but the instruction may not have been completed at that point in time. And you need to also handle have everything that's required to handle an exception and interrupt precisely if an exception and interrupt needs to be handled before retiring the instruction, right? And we discussed that, right? How do we know which instruction is the oldest? That's basically, you have a separate pointer that says this is the head pointer in the reorder buffer. We're going to go through an example in a little bit, hopefully. So basically, you need val bits to keep track of the readiness of the results and find out if the instruction has completed execution, right? So I'm going to give you an example. Yeah, one of your colleagues says we basically have a queue. Yes, absolutely. This is a queue. It's actually a circular queue because it needs to be in hardware, and in hardware you need to implement a circular queue, right? Okay. So basically, reorder buffer looks like this. Let's think about it conceptually at a high level first. You write the result first to the reorder buffer when the instruction completes, and that's the function of this R stage over here now. And you write the result from the reorder buffer to the register file at commit time. So if you do this, the earlier picture becomes more beautiful or more aligned with precise exceptions. So basically, this second add, one cycle add finishes, it writes its result into the reorder buffer, and later instructions may take its result from the reorder buffer, which we will talk about. But it doesn't update the register file. Register file update happens only after this add becomes the oldest instruction in the machine, meaning at the head of the queue, reorder buffer queue, right? Same is true for the next instruction, next instruction, next instruction. You can see that the write back stage is sequential over here. Reorder buffer write stage is not sequential. Instructions write to the reorder buffer whenever they finish, basically, right? So we've preserved the sequential semantics. But now the question becomes, what if a later instruction needs a value in the reorder buffer? And things become interesting right now. Basically, we didn't write to the register file. The instruction complete execution. The result is not in the register file because this instruction did not update the register file. The instruction is not in the pipeline, so the result cannot be provided from the bypass paths or the forwarding paths we discussed in the last lecture. The result is in the reorder buffer. And if a later instruction is dependent on this add over here, how do you get the result? Well, now the later instruction should read the reorder buffer, right? So we have added some complication. The value written by instruction can be inside the register file or inside the reorder buffer or inside the pipeline registers, right? After it's produced, of course. And we're going to see this complication a little bit. So, of course, one option is stall the operation, stall the pipeline if it needs the value in the reorder buffer, but that's not a good idea. The better option is to read the value from the reorder buffer, and then the question becomes how, right? So we're going to see that. So basically, how to access the reorder buffer becomes a problem. As I said, a register value can be in the register file, reorder buffer, or the bypass and forwarding path. So you can see that whenever an instruction is decoded, it accesses the register file. Okay, it can access the reorder buffer, and it also may take the value from the bypass paths. Basically, because the producer instruction may be in the pipeline, then it gets the value from then the dependent instruction should get the value from the bypass paths. If the producer instruction has finished, completed execution is functioning it, but has not yet retired, then the value of the register is in the reorder buffer. So the dependent instruction should get the value from the reorder buffer. And if the producer instruction is not in the pipeline, and if it has updated the register file, and there are no other instructions writing to the source register that the instruction that's being decoded is sourcing from, then you can get the value from the register file. So you basically access these structures concurrently, two structures concurrently, and you have a multiplexer. Also, bypass paths can actually provide the value as well. Okay. Okay. So basically, let's take a look at how this happens. So I think there's one question. There are a lot of questions today, which is good. Doesn't the reorder buffer now change the latency of every instruction towards the low worst case latency? Well, not exactly, right? It changes the finishing latency to the worst case latency. If there's no instruction that is taking 650 cycles, every instruction can take one cycle. If all of your instructions are one cycle instructions, basically the picture is very different from the worst case latency, right? Think about the common case. Okay. Okay, so basically, let's take a look at what these register file and reorder buffer accesses are. So I'm going to introduce some more terms. I'm going to take a break after the end of this 15A because it becomes, I don't want to disrupt the flow because it's going to be important later on also. But basically, register file access is easy, actually. Register file, you index, if you remember, this is random access memory. We didn't call it random access memory, but it's actually a memory structure with random access memory. You index the register file with the register ID, which is the address of an entry. But reorder buffer is a bit different. Reorder buffer, remember, instructions are queued in terms of when they entered the reorder buffer. If you want to search for a register ID, you have a problem. You need to search the structure with a register ID, right? Which is part of the content of an entry. So at this point, I'm going to discuss basically what this means with an example, hopefully. So let's try how we're going to do that. I'm going to share my other screen over here. So I share my screen. Let's hope that this works. I'll start broadcast. I need to do that. Okay. I guess, are you seeing my share? I guess you're not seeing my sharing because I probably need to stop sharing this one. Okay. Okay, I stop sharing that one. I start broadcast here. Let's hope that you're seeing this one. Okay, good. Now you're seeing my iPad. I guess yes. Now I need to go to, okay, this notes. Okay, so basically, let's take a look at what happened over here. Maybe this is a better way of laying this out. Okay, not necessarily. Forget that. So let's take a look at what happened. This is our register file. And this is our, maybe I will put the reorder buffer somewhere over here, even though we're going to access it concurrently so that we have more space. Okay, so basically, register file has register 0 to register 7, let's say. And whenever you an instruction needs, let's say you have an instruction that you fetched that requires the register 3 and register 5. And there are some instructions in the pipeline that are writing to register 3, for example, right? And they may have finished. The data value may be in the reorder buffer, right? So let's actually go through the reorder buffer a little bit. Reorder buffer is a circular queue, as I said. You have an oldest pointer. This is the oldest instruction in the machine. And you have a youngest pointer. It could be a tail pointer also. That's the youngest instruction in the machine. And you may have, for example, let's say, I don't know, I'll just make it up, 128 entries over here. In recent Apple M1, actually, it's much larger. I don't remember how much it was, but it's hundreds of entries, for example. But basically, this basically is a bookkeeping structure that tells you all instructions in the program order that are in the machine. And you basically have a valid bit, whether actually the reorder buffer entry is valid, and all of the instructions that are in the machine should be valid over here. I'm not going to go through that. But basically, if the instruction that's being decoded needs register 3, for example, the value of register 3 can be in the register file. There's some value in the register file, right? But it can also be in the reorder buffer, right? But how do you get it in the reorder buffer? Get it from the reorder buffer becomes a problem. So, for example, there might be an instruction that's writing to a destination register, and then you need to have a valid bit for the destination register valid if it has written to the destination register, and then you need to have a destination register value over here. So there are 3 fields. And now what you need to do is to check if anybody in the reorder buffer is writing to register 3. I'm going to switch to some other color over here. So for example, this instruction over here in reorder buffer entry, I don't know, 35, is writing to register 3. Okay. Now, register 3 has some value over here, but register 3 also has some value over here. Okay. And then you have a pipeline over here, which we should ignore basically. But what does this mean right now? Basically, you have an entry in the reorder buffer that's writing to register 3, and register 3 is valid in the reorder buffer. which means that the instruction that is in reorder buffer entry 35 has written to that value, and it has some value. It has some, I don't know, 567. I just made it up. It doesn't matter what value it has, right? You really want to get the value of register 3 from the reorder buffer, right? Why? Because the value in the register file is stale. It's the old value. Because you have some instruction. Okay, let me actually. This is, let's say, the young instruction. An older instruction, let's say this is an add instruction that's writing into register 3. We don't care what the sources are, but we're writing this older instruction is writing to register 3. You want the value to come from this, and then this is a destination register, which you don't care about also, but you want the value to come from this older instruction, which is here in the reorder buffer. The value in the register file is not updated yet because this instruction that is writing to register 3 is in the machine. It didn't retire because there are some earlier instructions that are supposed to finish, but they did not finish yet. Right? So this instruction finished execution that is writing to R3, but it didn't update the register file yet. The incoming instruction should not get the value from register 3 in the register file. It should get the value from the reorder buffer. But of course, the question is, how do you do that? Now, this becomes complicated because you need to search the reorder buffer. So you're searching for register 3, right? So you have basically the ID of register 3. Now you need to compare it to all of these destination registers that are potentially in the reorder buffer. Basically, I need to have a comparator. Register 3 compared to the register ID here. Register 3 compared to register ID over here. Now you get the point, hopefully. Register 3 compared to register ID here. You need to have 128 of these comparators, which sounds bad, clearly, right? Because now what happened was you need to get the value of register 3, but you don't know where it is. Because the instruction, any instruction that's in the machine may write to register 3. It may be in any location, the reorder buffer. So you really need to do this content addressable search. So this is called a content addressable memory. Meaning you're searching the contents of the reorder buffer entries based on one potential thing, which is the destination register ID, right? Okay. And also you need to make sure that the destination register is valid. If it's not valid, then you need to wait for this value. You can get the value from the bypass path, right? If it's not valid, so if it's valid, it means that the instruction that's writing to R3 has finished execution and it can get the value. Fine. If it's not valid, then that means that the instruction has not finished execution. It's in the pipeline. So you can get the value from the bypass forwarding paths. So this reorder buffer actually tells you information about where the value is if it's not valid. But of course, there's a complication, as I think some of you are asking right now. Yeah, I think I need to read. Yeah, how do you deal with this possibility that multiple instructions write to register 3? And that was the question I was expecting, basically. And that's certainly a very valid question. Your search becomes more complicated, meaning your search is not just a search for register 3. You're really searching for the youngest definition of register 3. Remember that this is the oldest instruction, this is the youngest instruction. You should get the value of register 3 from the youngest possible instruction that's writing to register 3. So if there's another instruction here that's writing to register 3, and it basically should get that value, right? Now, there's also a very interesting thing happened. This is a form of renaming now, right? You may have multiple instructions in the machine that are writing to register 3, right? Enabled by this reorder buffer. They will write their results to the reorder buffer first, and then they will move their result to the register file. And any instruction that comes later sources the correct register 3 because it gets the value from the youngest possible instruction that's older than itself, right? Hopefully that makes it clear. Basically, this is a content addressable search, but it's an ordered search also. And the comparators are actually a priority order comparators. So it's not an easy search, if you will. Okay, so hopefully it's now clear how the register file and reorder buffer operates. Basically, okay, let me actually talk a little bit more about how this operates because it's going to be important. So we search from youngest to oldest and takes the third match. Yes, absolutely. You search from youngest to oldest and takes the first match. Okay, there's one more question. What is the difference between valid bit and destination register value? So valid bit means that you actually wrote the value, right? You need to basically distinguish from whether or not you have written the value into the destination register. Okay, and value is the value itself, of course, right? Because once you write the value into the destreg value over here, you also set the valid bit. Okay. If it's invalid, it means that the value is being generated in the pipeline. The instructions in the pipeline is not written to the register reorder buffer yet. So it's going to you can get the value from the bypass paths, from the forwarding paths. Okay, so let me finish this with looking at the operation of the reorder buffer a little bit. Basically, once the oldest instruction finishes, you check for exceptions. Of course, basically there's some finite state machine. There's some control logic that checks every cycle the oldest pointer and the entry over here. If it finishes, what does that mean? If that means that it's valid, first of all, that entry is valid. Well, hopefully, if the oldest pointer is pointing to it, then it should be valid. Its destination register is valid, or if it's a store, if its store address and store data are valid, etc. I'm not going to go into all of the details of different types of instructions over here. Let's assume R-type instructions. Now, if it's valid, then it's finished. It also checks whether there's an exception from the instruction. And if this exception is set to none, then you can take the destination register value and write it to destination register ID, right? Whatever that ID specifies. Okay, assuming that the instruction has written to the reorder buffer, which means that it's valid. Its entry is valid, and also the value that's writing is valid. And what do? You basically advance the oldest pointer, and that's what would answer the question that your colleague asked over here. You advance the oldest pointer to here, right? Now this entry becomes invalid. It becomes 0, right? So that's the global valid bit, right? Global valid bit means whether or not you have allocated something in the reorder buffer, because it's a limited size structure. You may actually have zero entries in the reorder buffer if the pipeline is just flushed, for example. Okay, so that's the operation of the reorder buffer. Hopefully it's clear, or it's more clear right now. And we're going to solve this content addressable problem right now. Okay, let me switch back to here. So basically, I've given you that we need to search the register file. It's easy. It's an index. But searching the reorder buffer for the latest definition of R3 is not easy. It's content addressable memory. It's a difficult search. And also, you have the bypass paths. But now you know how to get the value from where, right? So hopefully this is clear. But now we have a content addressable memory, which is not efficient. So we're going to fix that problem. Let's see how we fix that problem. Basically, how do we simplify the reorder buffer access, right? And that's the idea. Okay, my iPad is talking to me for some reason. Okay. Basically, the idea is to use indirection. And this is a very common idea. If you're searching two concurrent structures at the same time, you can serialize the search. So if you're searching register file and reorder buffer at the same time, and that's causing problems, well, why don't we serialize the search? Meaning, let's access the register file first, and we have valid bits in the register file now. Check if the register is valid, and access the reorder buffer next if needed. And we're going to do that. I'm going to also demonstrate that. Basically, now reorder buffer does not need to be content addressable, as we will see. So basically, you access the register file first, and we have valid bits with the registers, as with scoreboarding. I didn't show them in the previous picture because I thought it was obvious, but we're going to see that those valid bits again. If the register is not valid, that means that there's some instruction in the machine that's writing to that register file, that's going to write to that register. But now the register file stores the ID of the reorder buffer entry that contains, or that will contain, the value of the register. So we're going to add another entry to the register file saying which reorder buffer entry this register is going to be produced by. Or you can use the data field. Basically, you can be smart and you can use this, use the already existing entry to point to the location in the reorder buffer that's going to produce the value of this register. So this is smart, this indirection clearly. So now what we've done is we're mapping the register to a reorder buffer entry. Register file maps the register to a reorder buffer entry if there's an in-flight instruction writing to the register. This is also going to be called renaming. Essentially, we're renaming the register. And this is going to be very important for out-of-order execution, which we're going to cover partly today. So let's take a look at that basically. Actually, this is used in Pentium 3. This is real. They call it a register alias table. Basically, this is actually a mapping table. This basically tells you where the register exists. This is register 0 or EAX in x86 terminology. This basically says register 0 is mapped to reorder buffer entry X over here, which means that there's some instruction in the pipeline that's going to write to EAX. And EBX is mapped to a real register file. It's called a retirement register file in Pentium 3. This is also Pentium Pro, basically. It should be Pentium Pro, actually. But basically, this basically says that there is no instruction in the pipeline that's going to write to EBX register, so you can get the value from the register file. Okay? So let's take a look at this operation a little bit. Let me go back to my iPad and share the screen if possible. Okay. The interfaces are not that great over here. So, oh, was I not sharing my screen? I thought I was sharing my screen. Okay, let me. So so basically, hopefully you saw that I was sharing my screen, right? So basically, we talked about this part. We're going to use injection. We access the register file first. We access the reorder buffer next. And reorder buffer does not need to be content addressable in this case. Okay, somebody said, yes, that's good because I cannot tell whether I was sharing my screen. Sorry about that. Okay, so I'm not going to repeat all this information. Now I want to stop sharing the screen and switch to this screen over here. Okay, start broadcast here. Okay, now I'm seeing that screen. So now we're going to fix this picture over here. So we had this messy content addressable search. We're going to change that, hopefully. Oh, that's not what I want. How do I add a page over here? Well, add page. Okay, below. Below sounds good. And okay. This doesn't need to be that complicated, right? Okay, squared paper. Why not? Okay, basically, if you look at this picture, we have this register file and the reorder buffer. We're going to have the same things again, but except now I'm going to make the register file a little bit different. I'm going to have val bits. I'm going to have the value. I'm going to also have the pointer, or I can call this the tag. You're going to see what this tag means later on, but it's essentially the pointer to the reorder buffer entry that's going to produce the register. And now I'm going to have the reorder buffer, just like before. Nothing is different over here in the reorder buffer. You have the same entries, and you have the oldest and the youngest. But what is going to be different is whenever an instruction gets decoded, let's decode this instruction. That's writing to R3. Basically, ignore what happens with the sources. I'm going to show that in the next instruction. Initially, all of the registers are valid. They have some values that we don't care about, and you can ignore the tags. But whenever we're writing to register 3, what we're going to do is we're going to allocate this instruction in the youngest entry in the reorder buffer. So basically, this add is going to go to, I don't know, let's say entry 68. I just made it up again. We're writing to register 3. So register 3 over here is going to become invalid. At the time we're decoding this instruction. Okay, it'll become invalid. We're going to say that the value of register 3 is going to be produced by reorder buffer entry 68. Okay, so we're going to change this pointer or tag to 68. So this means that after I decode this add instruction, what I'm saying is add instruction, there's some instruction that's going to write to register 3 in the pipeline. And that instruction is in location 68 in the reorder buffer. So whenever some other instruction comes into the pipeline, they can get the value from location 68. And we're going to see the usefulness of this later on. Okay, so now what happens? Let's take a look. Let's assume that this add finishes. It writes its value. So this is valid, of course, after you decode this instruction. It writes register 3, and it's register 3 becomes valid after this add finishes. And it writes value, I don't know, 576. That was the value I had. And it doesn't have an exception, etc. Later, we have another instruction, let's say add, after so many instructions, meaning that the youngest pointer should have advanced to somewhere over here. Okay, this is not the youngest anymore. Okay, and this other instruction add comes in. It's going to source R3. I'm going to ignore what it writes to. What it's going to see is this. It's going to see basically access only the register file first, right? We're not going to access the register file and reorder buffer concurrently. This instruction is going to access only register file first with the source register. It's going to see that source register is not valid. So value we don't care about because the source register is not valid. But we know that the value is potentially in location 68 in the reorder buffer. Now we can take that pointer, index directly into the reorder buffer, because reorder buffer entries are 0 through, I don't know, again, 127, let's say. Now we go to 68. We don't need to search the reorder buffer anymore because we have this index directly into the register that is producing the value. And now we can get the value from there, right? Okay. So it's not simpler right now. You don't need to do this content addressable search across the entire reorder buffer anymore, because we actually have an index into the reorder buffer entry that is going to produce this R3 at this point in time. Now, what might happen? Let's take a look at another example over here. This add, let's extend this over here. I'm just taking the liberty of making things a bit simple, but let's assume that. Actually, let me make it a little bit different over here. Let's assume that there was another add. There was another add that wrote to R3 before here. Okay. If this add didn't exist, clearly, if this add didn't exist, what we did was correct. Okay. So if this add, now ignore this one over here. Let's assume now we have another add that's going to write to R3. And there are some other instructions here. Ignore the sources. What this add will do is it's going to allocate itself in the reorder buffer. It's going to write to R3 over here. It's not valid at this point, but it's going to change this pointer from 68 to, I don't know, 125, let's say, wherever it's allocated. So now the later instructions that are coming into the machine will not get the value from location 68, but they will get the value from location 125. And this makes sense. This is what really should happen in program order, right? Does that make sense? So a later instruction right now, a later instruction that does add sources R3. Now it's going to access the register file, get the tag 125. That's the reorder buffer entry that's going to produce the result, and check this location and not the older definition of R3. And that's correct, because you should really get the value from the youngest instruction that's writing to R3 that's older than you, right? So hopefully this makes it clear that you can link the instructions using their reorder buffer IDs. And we're going to call them tags when we talk about out of order execution soon. Okay, there's one question. How do we make sure Rob never overflows? Well, basically, whenever the oldest pointer is equal to the youngest, you basically need to stop the machine. You don't decode more instructions into the machine. You stall the machine basically at that point. Why don't we just overwrite the old entry in the ROB? I don't know what that means, but you cannot just overwrite the old entry in the ROB when because there's some instruction over there in the machine, right? You need to make sure that the old entry writes into the destination register first before you evict that old entry. So there could be cases when your reorder buffer is full because the oldest instruction machine is not finished yet. It's waiting for a memory access, for example, and your reorder buffer is completely full. At that point, you need to stall the machine. No instruction can be decoded into the machine, right? Okay. So let me actually. What if instead of add there was a longer instruction and next one already depends on the written reg, which isn't ready yet? Do we have to stall? Yeah, I don't know what that means, but. Yes, basically, if you don't have the value yet, you need to stall or get it out of the forwarding paths, basically. There's another question. Why is desreg v invalid at entry 125? Whenever you decode the instruction, it becomes invalid first, right? That desreg becomes valid when this instruction finishes execution and writes into the reorder buffer. Okay, so I'm going to now switch again to the slides. Okay, so hopefully now you understand the principles of the reorder buffer. There are a lot of cases, of course, that you can imagine and you can simulate the machine in your head. But once you understand the principles, I think all of them are relatively simple. Okay, so I already said that reorder buffer in Intel Pentium 3 is very similar to what I showed you earlier. But let me actually talk about register renaming. Essentially, what we have done is register renaming the reorder buffer. As I mentioned earlier, output and anti-dependencies are not true dependencies or dependencies because the same register refers to values that have nothing to do with each other, right? And they exist due to lack of register IDs or names in the ISA. Now, what we've done with the reorder buffer is we have renamed the reorder buffer entry that will, we have renamed the register ID to the reorder buffer entry that will hold the register's value. So basically, we have taken the architectural register ID, renamed it to reorder buffer entry ID. And now all instructions that are sourcing that definition of the architectural register ID can source it from the reorder buffer entry ID from the linkage that we have provided through the register file. And this is going to be essential to out-of-order execution. Architectural register, in other words, architectural register ID is renamed to some physical register ID. You can think of reorder buffer as storing some physical registers, right? It has 128 entries. In modern machines, it may have 512 entries, for example. Basically, you're potentially storing 512 registers, which is not the case if you have a small architectural register file. So this is, you can think of this as a micro architectural register file, if you will, except it's implemented as a reorder buffer. So after renaming, reorder buffer entry is ID is used to refer to the register at that point. So you don't refer to the register as R3 anymore. You refer to the register as reorder buffer entry 68, for example, or 125, as we have seen. So that's a good question. Is there a performance benefit to the reorder buffer? I mean, not exactly. What we're doing right now is really providing precise exceptions, precise semantics, and try to provide the benefits of forwarding the values in a good way. So there are really no performance benefits the way we discussed it so far. But later on, when we introduce out-of-order execution, the whole machine will provide performance benefits, as we will see. So renaming, the register renaming concept provided by the reorder buffer will lead to performance benefits later, but not right now. So that's a good question. But basically, what we have done, the renaming through the reorder buffer eliminates anti and output dependencies. It gives the illusion that there are a large number of registers, as many as the number of reorder buffer. And also now you can have multiple register trees that are present in the machine, right? You don't, in an architectural register file, you have only one register tree. In a reorder buffer, all of the instructions may be writing to register 3. Right? Of course, that's an extreme situation, which is not desirable probably in a programming perspective, but it could happen. Okay, we've discussed true anti and output data dependencies. This way, we've eliminated the anti and output dependencies by renaming the registers. These registers, this register 1 is now reorder buffer entry something, right? It's not register 1 anymore. And this register 3 is reorder buffer entry something, and the instruction that's going to source register 3 is going to get the value from that reorder buffer entry something. Right? Okay, so I'm not going to go through this example because we're going to actually go through this example later on when we discuss out-of-order execution. But you can do this example on your own. Assume that a register file is a pointer to the reorder buffer entry that contains or will contain the value if the register is not valid. And reorder buffer works as described before. Then the question becomes, where is the latest definition of R3 for each instruction below in sequential order? You need to kind of simulate what happens in the machine that we described earlier. And this is not a very difficult question, if you will. For example, this load will write to reorder buffer entry 0. So this register 3 will be renamed to reorder buffer entry 0. This register 3 will source, this instruction will source to reorder buffer entry 0. This multiply will write to reorder buffer entry 2, 0, 1, 2, because you were decoding instructions in order. And this R3 will, this multiply will source register 3 from reorder buffer entry 2. This add will write to reorder buffer entry 4. And clearly you can see that there's no R3 that's being sourced at that point, after at least in this program over here. So basically, it's a very simple approach that you can think intuitively about, and you can simulate in your head even without drawing, as I just did. Okay, basically what we have constructed this in-order pipeline with our reorder buffer. What we have is a machine that can do in-order dispatch. We're going to describe the definition of dispatch later on. Basically, you decode the instructions in order. You complete the instructions out of order. Basically, this point is out of order. But you write the instructions to the reorder buffer out of order. But you retire instructions, meaning update the architectural state in order again. Right? And you need to get the value from the in the decode state, either from the register file or the reorder buffer in an indirection way, or from the bypass paths in any of these places. Okay, basically at the decode stage, we access the register file and the reorder buffer, allocate entry in the reorder buffer, check if the instruction can execute. If so, we can dispatch the instruction. We're going to see that check if the instruction can execute. Because if the values are not available, the instruction should not be able to execute, right? That's basically you stall if the value is not produced yet, right? Clearly, we still stall if the values are not ready. Execution stage, instruction can complete out of order, as we discussed. And completion stage, we write the result to the reorder buffer. That's this R over here. And in the retirement or commit or write back stage, we check for exceptions. If there are none, we write the result to the architectural register file or memory. Otherwise, if there are exceptions, we flush the pipeline and start from the exception handler, as we discussed earlier. Okay, so let's talk about the trade-offs of the reorder buffer before we conclude and then hopefully get to the beginning of the out-of-order execution a little bit at least. So advantages. Now, this is a very conceptually simple way of supporting precise exceptions. It's actually the simplest way conceptually, in my opinion. Other approaches are not as simple as reorder buffer, as you can see from other videos if you're interested. It can eliminate false dependencies through renaming. Basically, the big benefit of what we have seen with reorder buffer is renaming of a register to a reorder buffer ID. Okay. The disadvantages, of course, are reorder buffer needs to be accessed to get the results that are yet to be written to the register file, right? And this leads to either a content addressable memory, which we said is a bad idea, or indirection. Regardless, it leads to increased latency and complexity, but indirection is at least easier to handle, whereas content addressable memory, as we discussed, is a lot of searches. But there are other solutions that aim to eliminate the disadvantages of the reorder buffer, like the history buffer, future file, and checkpointing, which we're not going to talk about, but see the suggested lecture videos from 2015, as I will point soon. Let me actually handle some questions very quickly. How do we stall for a specific instruction if the access register is about to get updated but cannot be forwarded yet? Basically, you figure that out from the forwarding logic, as well as the reorder buffer. You need to think about that a little bit. So when do we use data forwarding bypassing directly from the pipeline, and when do we search the reorder buffer? Essentially, you always search the reorder buffer if the register file indicates so. And if you get an invalid result in the reorder buffer, that means that the result may be coming from the forwarding paths, right? So somebody asks, are bypass paths even necessary? We can just write the result to the reorder buffer as soon as it's available. Well, as I said, if the value is not written to the reorder buffer yet, you cannot. So this is a good question, I think. Basically, it depends on how you write to the reorder buffer. Yes. So you may potentially eliminate the bypass paths if you write to the reorder buffer right away. But there may be reasons why you may not want to do that also, because it may complicate the pipeline, right? But that's a good question, basically. You may want to think about that. And in out-of-order execution, this is all going to change a little bit. Okay, so basically, this is essentially, if you're interested in state maintenance and precise exception, and this is a topic that has fascinated many people, actually, I would recommend looking into lectures that go into more detail, like history buffer, future file, and checkpointing. These are actually really interesting topics that are more broadly applicable to checkpointing state in general. So this sort of thing happens in distributed systems also, for example, not just in the hardware of the processor. This sort of thing happens in software checkpointing as well, for example, when you need to maintain state, precise state. And if you're interested, you can also watch last year's lecture as well. Okay, I also have suggested readings for the interested. We've actually, this is not suggested, the middle one's required, but there are also a bunch of suggested readings over here. If you're interested, you can do them. And you can also look at the backup slides. I have a lot of backup slides describing the other approaches to the problem. Okay, so I think at this point, let's take a quick break. Let's be back in 10 minutes. That's 15:49. And we're going to do an introduction to out-of-order execution, because it's going to be important after this context that we have provided. And then we're going to cover out-of-order execution in more detail next week in terms of exactly how it works.